Okay, so we're going to talk about the derivative of trigonometric functions. There is a proof in the book, and we're going to go through it, but you will not be expected to come up with something like this. I just wanted to use this animation to show you what the derivative of sine will be. So I have the graph of sine of x, and as you can see, it looks like a wave. In here, the sine of 0 is 0. For what number the sine is 1, and you remember that that number is pi over 2. Pi over 2 will be some number between 1 and 2. So remember that the graph of sine of x, if I'm graphing it on an xy coordinate plane, the units of x are radians and not degrees. That's why you don't see a 90 here. We're using radians. Again, when is the sine of x 0 for x equals pi, which is the number 3.14, so that's why this curve intersects the x-axis at a point that is bigger than 3. Remember that this number will be pi, and so on. So this is just to remind you what the sine of x looks like. So I'm going to pick a point on the sine of x, and I'm going to have the slope triangle for it. Remember that the slope triangle will be, if I draw the tangent line at that point, and then I'm trying to calculate the slope of it. Now you can see the calculations here. This will be the value of f prime at that particular point. This is the difference of the y's divided by the difference of the x's, and that gives me the slope here. And this is the graph of this slope triangle from this point here. And you can see the difference of the y's is 0.96 and the difference of the x's is 1. So I'm going to start moving this point along the curve of the sine of x. So you can tell that the slope triangle is unique for every single point, which is something that we knew. And this is true for all the functions that are not linear. Only in the linear cases, this slope triangle is always the same, no matter where you are on the line. So now that I move over here, the slope triangle have changed, and now f prime for that particular x, that particular s is negative 5.35, is 0.595, and in here I'm graphing what f prime will be. So I started with a positive number, but now this positive number is being we're reducing it because the slope is less than it was before. So as I'm approaching the top of the hill here, you can tell that the slope triangle is showing me a difference of the y's that is smaller and smaller and smaller and smaller. That's why this y is approaching the x-axis, because the value of the y coordinate is approaching 0. So what's going to happen when I have that point all the way on the top? As you know, the slope will be approaching that value of 0. I can't have it exactly as 0, but you can tell that now the slope is almost 0, and that's why this line has a y coordinate of 0. So what's going to happen between this top of the hill and the bottom of the valley here? The slopes, as you can tell, are going to be negative slopes now, and that's why the y coordinates for these points are negative. This is the graph of f prime, and then it's more negative, and it's more negative, and it's more negative as I'm moving my x. But then at this point, it's gonna stop decreasing. That's the most negative that you can get, and then as I keep going, it's gonna be less negative and less negative and less negative and less negative until I reach the value of 0 again. So this is a good graph, not to show us only what this derivative of sine is, but also to get a feeling of what would f prime would look like if I know how f looks like. And this is something that we're going to do in the future as well. So this is common attractions. And then the slope again turns positive, a lot more positive, a lot more positive, a lot more positive, and that's going to reach its maximum, and then it's going to be less positive and less positive and less positive until I reach the top of the other hill, and that will be 0 again. And then I'm gonna do that one more time. Now it's negative, it's become more negative, it's become more negative. It became the most negative that it can get. And then it's gonna be less negative and less negative and less negative, and then it's gonna reach 0 again. And then I can continue doing that as well. So the result, let's see what we have here. F prime, when I take the derivative of sine of x, when I'm calculating the slope of the tangent line at every single point, that value is also forming a wave, and it just happens to be, let's try to find out what this wave is. At 0, it's worth 1, and at pi over 2 is worth 0, and at pi is worth -1. So what trigonometric function is that? Where I have the cosine of 0, 1. Oh, I just gave it away. Yeah, it is the cosine function. Ta-da! Okay, so let's check out the proof that we have on the book. Again, it is understood that the sine of x means the sine of the angle whose radian measure is x. We're talking about radians, and also an important thing to remember is that all the trig functions are continuous at every number in their domain. So remember, even something like tangent of x is continuous on its domain. Okay, so this is a picture of the animation that we just saw. This is the curve y equals sine of x, and whenever I have the slope of the tangent line being 0, then this marks the zeros on the function that I call f prime, that I give it away, happens to be cosine of x. So and here we are going to find out that that's actually the case. If I'm trying to find the derivative of a function, then I take the limit. This is one of the definitions that we have studied. This is the difference of the y's, all divided by h. So I only have to find this limit of this giant thing. I can distribute the h's in every single term, and conveniently I'm grouping these terms in this manner. Now from here I can see that if I'm going to find all these limits, one interesting thing that I see is that as h is approaching 0, what would be the limit of sine of x? Now let's remember what our constant rule was. Sine of x, there is no h present in here. So if I'm evaluating this limit as h is approaching 0, since this expression does not depend on h, I'm going to consider it as a constant. That's why the limit as h approaches 0 of sine of x is simply sine of x, because h is not present on this expression. This expression does not depend on h, so to h's eyes, this is a constant. And the same idea with the limit as h approaches 0 of cosine of x is just simply cosine of x. So this stays as sine of x, and this stays as cosine of x. And now the idea is to find what these limits are, and then we're going to be able to find what is the derivative of the function sine of x. On the next slides, it is shown that this is worth 0, and this is something that we have seen in previous sections, and this is one of those limits that I said that we have to remember them as facts, because they're going to be useful in some other calculations, and this is one of the uses. The same idea in here, as h approaches 0, if I evaluate, this will be 0, this will be 0, and I have 0 divided by 0, and you know that you cannot evaluate a limit like that. But we have shown using the squeeze theorem or the sandwich theorem that this limit is actually 1. So with this being 0, this term cancels out, and with this being 1, the derivative is simply cosine of x. Okay, so we have the first equation for derivative of sine of x. It will be simply cosine of x. Now, using the same method that you have seen in the previous slides, I'm not going to go over those slides because it is just important that you get the idea of this. If we work similarly, we're going to find out that the cosine of x is negative sine of x. and the derivative of tangent will be simply the derivative of the division of sine by cosine of x, I can apply the quotient rule and I can get the following result, that the derivative of tangent is secant squared. Not only the combination of the quotient rule, but also I'm going to have to use some trigonometric identities. So let's just remember what those are. I know that tangent of x will be sine of x over cosine of x, and cotangent is with the reciprocal. The other one that I need to remember are the Pythagorean identities, and those would be sine square of x plus cosine square of x is 1, and then 1 plus tangent square of x is secant square, and 1 plus cotangent square of x is cosecant square of x. So it is expected of us to remember all these derivatives to be able to do or to take the derivative of other functions that include these. So please study those like you did your times table.